Alrighty-o, ladies and gentlemen, 5.5. 5.4 was just an exercise. We kind of did something in class, so 5.5 is the next section, ladies and gentlemen. We interpreted a bunch of graphs, and now we're going to be looking at relations and functions and their graphs as well. I've got a bunch more stuff to show you, but let's deal with what we already know, okay? So first of all, we can identify a function from a list of ordered pairs, right? So you can tell from a list of ordered pairs, for example, if I gave you a list of ordered pairs, 2, 3, and then 3, 5, and then 4, 7, and then 5, 9, hopefully you'll be able to tell me whether that's a function or not. And I think that you guys know where you need to look, and it's actually at the x value, right? So the x, so the domain here, if I was going to ask you to state the domain, it would be 2, 3, 4, 5, and if I asked you to identify the range, it would be 3, 5, 7, 9. Now you can probably see a bit of a pattern there, and we're going to be looking for those patterns, but you should be able to identify a function from a list of ordered pairs because looking at the domain, they are all different x values, right? You should be able to identify from a table because if I put this in a table, it would be 2, 3, 3, 5, 4, 7, 5, 9, where this would be your x, that would be your y. You can see the same thing, right? Your x's are all different, so then we can see that it's a function. Now, if I looked at a graph here, right, and plotted these things up, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? If x was 2, y is 3. If x is 3, y is 5. If x is 4, it's 7. If it's 5, it's 9. You can see that you will also have a function there, and I'm going to show you quickly why, or how we to tell it off of a graph relatively easy. Okay, so why, first of all, do we use graphs? Primarily it's because it's easy to interpret. It's easier to identify trends and make extrapolations, right? So you can see trends, you can see if it's going up generally or if it's going down generally. You can make predictions, which we call extrapolate and interpolate. Remember, extrapolate means you go beyond the graph to look. Interpolate means that you can find numbers in between. So data on a graph is very, very effective. And as soon as we start dealing with graphs, or now that we're dealing with graphs, you will probably notice that they occur a lot more frequently than you may have noticed in the past, okay? Now here's a quick question I'd like to ask you. Are all functions relations, and are all relations functions? Well, all functions are indeed relations because they are a special type of relationship. All relations, however, are not functions. And we know this because if I showed you, for example, here, right now, if I showed you here a relationship between the height and the mass of 8 polar bears, you can see that they have a variety of different masses and they have a variety of different heights as well. But if I was going to plot this data, you'd see that there's 2 of them at 400 that have different values. So the height of would be 2.2 and then 2.6, but they both have a mass of 400 kilograms. So this indeed would not be a function, even though it is a relation. So yes for this and no for that, because all relations are not functions. Now, from a graph here, the vertical line test is something that is going to come up a lot, VLT. Now what that basically means is that a vertical line, it's telling a vertical line is not a function, okay? So if you can draw a vertical line and cross 2 points, then you don't have a function. That's basically it. If you can cross 2 points and it's on a vertical line, then it is not a function, okay? And let me just quickly show you an example. So if I had a graph that looked like this, and it was going down and across and it decided to curl up, boom, because I can draw a vertical line and cross twice, that is not a function, okay? This part is a function, absolutely, because you can't do it twice. So that's a vertical line test, okay? The next thing is to understand the difference between discrete and continuous data. Now, in this case right here, these are individual weights. So yeah, there might exist stuff in between there, but we don't have bears in between A and B. So this is discrete data as well, okay? If we look at something like, where am I here? How about the number of fishing boats anchored in an inlet? Let me see if I can zoom in on that for you. So number of fishing boats anchored in an inlet, right? So you can see that you've got at 9 o'clock, there's like 25 boats, right? And at 10 o'clock, there's 10 boats. And at 11 o'clock, there's 8 boats. And at 12 o'clock, there's 6 boats. And at 13 o'clock or 1 o'clock, there's 12 boats. So you can see that these are all pieces of data. This is indeed a function because there's no two values at any given time. There's only one number that identifies a number of boats at a specific time. So this is indeed a function. And these are discrete values, so we don't connect them. Okay, we just don't connect them. And we leave them as points. Here's another situation. Here you have a height of tide at the port. Well, look, at 9 o'clock they measured it to be 0.9. At 10 o'clock they measured it to be 1.2. At 11 o'clock they measured it to be 1.4. At 12 o'clock, so each of these points has measurements. But as you know, a tide doesn't sit there and all of a sudden go boop, jumps up, and then boop, jumps up again. It is a steady, continuous rise and fall. So these would indeed be continuous. How do you know whether something's discrete or continuous? It's logic. You use your brain, okay, and ask yourselves, can there be intermediate points? Okay, we've already discussed discrete and continuous, but that's the most basic. Let me go back down here. The most basic definition is simply, can you have points in between, right? Can you have points in between? So if you can, then it's called continuous. Function notation, ladies and gentlemen, function notation. So we're going to be looking at this a little bit more. F is just your F function, right? Let's just call it an F function. And, well, let's call it something else here. Let's call it a G function, okay? So G of X, right, is equal to something. So G of X is equal to 2X minus 1. We looked at saying, okay, well, find G of 2, right? Well, you know that means that you made the X 2, so it's 2 times 2 minus 1, which will be 4 minus 1, which is 3. Okay, now we're going to be looking at graphing these things, but what I'm also going to ask you here, you can put any number in for X and you just plug it in there, right? What if G of X is equal to 5? Okay, I'm going to ask you actually to find X now, right? So what you do is you take this thing, you take G of X equals 5 and put it in there. So you're going to have 5 now, because that's actually your G of X, right, is equal to 2X minus 1. And from that, you should be somewhat comfortable graphing, or sorry, not graphing, but finding the solution to this equation. Okay? Now, please understand plus 1, so you get 6 is equal to 2x. And the last step is that you divide by 2, and you get x is equal to 3. Okay? So this is how we do function notation. But what about if we're looking at graphs? Here is another graph. Okay? This function is g of x as well. Well, let's say that I wanted to find g of, let's say, 3. Okay, well, I just made x equal to 3. Now, understand that this graph right here is the g function. Okay, it is the g function. So, where is the g function when x is 3? Here, let me zoom in on this a little bit for you if I can. Where is the g function when x is 3? So you look along here, x-axis 3. Okay, now you go up. Oh, look, the g function is at 6. The y value is 6. So it's 6. Okay, think about where's g of 0. See if you guys can find that. G of 0. X is 0. 4, 5, 6. So it's 4.5. How about g of negative 1? X is negative 1. Negative 1. It's 4. There you go. All right. Now there's another thing here. Okay. Find x. Here I'm going to do this. Find x if g of x is equal to 7. Function itself. The function is up at 7. Where's 7? 7 is right here. Okay. There's my function. What's the x value? 2, 3, 4. So x is equal to 5. So that means that g of 5 is 7. This is about function notation, people, okay? It's about function notation. You have to kind of be comfortable interpreting the graphs and reading stuff off the graphs. Let's try again. Find x if g of x is equal to, let's try 5. So this is the function g of x. This is a g function. Where is it equal to 5? Well, we're looking at the y value. So 5 is right here. We go over. Boom. What's that value? That's x equals 1. So x is equal to 1. So again, if you took this, you could say g of 1 is equal to 5, right? That would be the function notation part. So I'm going to leave that alone for now and do a couple other things here. Hold on, let me get you back to the right zoom. All right, now domain and range notation. Yes, this is a little bit funkier. Now we'll be able to figure this out no problem. Now with discrete data and continuous data, it's a little bit different, right? So with discrete data, right, the domain, if you want to find the domain, you just list all the x values, right? It's not that hard. You just list all the x values. And then for the range, right, you list all the y values. Okay, so when we're looking to identify the domain and the range for discrete data, very easy. All you do is identify the x values either from your tables or from your ordered pairs or even off the graph if you want, okay? Just give me all the x values for the domain and then all the y values for the range. Now, with continuous data, ladies and gentlemen, with continuous data, it's significantly different, okay? Because now, we'll look at this, okay? Let me give you a couple examples here. If we're looking for the domain, you just list all the x values of each individual point, right? If we are looking for now the domain and range, what we have to do is realize, well, if this is continuous in between here, right? I want to identify everything in between here, and I can't start putting all the decimals and all the fractions in there because there's just an infinite number of points. So we identify intervals now, okay? We're looking at identifying intervals. So what we do is we have to understand a little bit about inequalities, okay? In particular, we have to understand that if I say x is greater than or equal to 2, then you can plot that on a number line like this. For example, 0, 1, 2. We put a circle here, and greater than 2 is that way, right? So what we're going to be looking at is identifying domain and range in a bunch of different types of questions. And hold on a sec here. What am I going to do? Yeah, I guess I'm just going to have to draw a couple things here. So let's have a look now at domain and range. All right, so here we go. Here's the first situation. If I have a point right here, that point is 1 and 2. Okay, now if I have a line that's going this way now, okay, you need to identify the domain and the range from these things. So what you do here, let's zoom in a little bit so you guys can see. What we do is we look at our starting point. This has a point here and it's going forever in that direction. So my domain is my x value and my range is my y. The domain starts at 1 and then it goes forever that way, right? It goes forever to the left or to the right. So all numbers bigger than 1. So we say x is greater than or equal to 1. And if we have the range, well, it starts at 2 and we're going above, so that's going to be greater than or equal to 2 as well, or greater than or equal to as well, because greater than means above. So let's think about this. This is greater than or equal to if you're going up this way, right? This is less than or equal to if you're going to be going down. It's going to be greater than or equal to if you're going this way, and it's going to be less than or equal to if you're going that way, right? So y is greater than or equal to the number if you're going up, y is less than, x is greater than, and x is less than. That might be a little bit confusing, but hopefully we'll get it sorted with a few more examples here. Let's try again here. So if I gave you a point right here, let's go -3 and 2. And then my line's going down like this. Okay, so let's say it's -3 and 2. So the domain is your x, and the range is your y. So the x value is -3, and the y value is 2. So the x values, are they getting bigger or are they getting smaller? The x values are getting bigger, so it's greater than or equal to. Now we look at the y value. The y value is greater above and less than below. So in this case, it's below the 2, so it's less than or equal to 2. Oh, I already got the 2 there. I don't need it twice. Okay, if you want, I'll give you one more here quickly. Let's look at this right here, and let's go back. There you go. So this point right here, let's call it 3 and -2. And let's identify the domain and range for that. Okay, so think about it for a second. Domain is your x. It starts here and goes that way. So x, y, 3, -2, less than or equal to, and greater than or equal to. Because the x's are less than 3, and the y values are greater than -2. Okay, so this is one type of domain and range question where you are bounded on one side, right, and it goes forever in the other. Okay, now let's look at another one. So let's slide it over here so I can see the thing. Now, boom, diddly boom, diddly boom, boom. Let's say we go from here to here. No. Let's say this point is -2, -1, and this point is 2, 2, or let's say 3, 3. Okay, now we're looking to identify an interval. It has a beginning and an end. Okay, it has a beginning and an end. So if you look at the x values, they're going from here to here, right? From -2 to 3. So if we're looking at the domain and we're looking at the range, the domain is the x, and this is how we set it up every single time, okay? If you're trying to identify an interval from a lower number to a smaller number, always go from lower to small, bigger, okay? Smallest to biggest. We put the smaller number first, and we put the larger number over here. Now we're looking for x's in the middle, and if you set it up this way every single time, it's always going to be less than or equal to, less than or equal to. Another way that you can do this is simply say, okay, x is going to be greater than or equal to -2, and x is going to be less than or equal to 3. Now, these are two separate intervals, or these are two separate things, okay? And they combine to give you this. Look, x is greater than -2. X is greater than -2. X is less than 3. X is less than 3. This is just a conventional way to write it, much prettier. Now let's think about the range. It goes from -1 all the way up to 3. So -1 in the middle, or on the left side, and the larger number on the right side. Y in the middle, always less than, less than. Okay, let me try another one here for you guys. How about this here? And we'll make this -2 and 3. -2 and 3. And we'll make this one 2, -5. So let's identify your domain. Let's identify your range. Okay, so x's go from here to here, from -2 to 2. X in the middle, boom, 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 boom. Range goes from here to here, from -5 to 3. -5 to 3, y, boom, 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 boom. Okay? Now, I'm almost done here. Let me just do a couple more examples of different situations. What happens if you have a graph going all the way across? It goes forever that way and forever that way. It covers all your possible values that exist, right? So in this case, what we do is we simply write down, and it's not x in both cases, it's what we call y. Now this is symbolic, this is set notation, okay? This means that your x is an element of all real numbers. Y is an element of all real numbers because they go forever in both directions. All the x's are covered, all the y's are covered. That means that you can have any value, not just integers, not just fractions, all real numbers. Okay, yeah, that's basically it. Sometimes you have a function that goes forever in one direction, but not the other. So this, say, goes up to 1 and down to -2, right? But it goes forever that way and forever that way. So in this case, what would be your domain, right? Your domain, because it goes forever in the x direction, is all real numbers. Your range goes from -2 to 1. So -2 to 1, y in the middle, boom, 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 boom. That's it. Okay? So there's a lot of funky type of questions. I can give you another one real quick here. If we put a circle in here like this and said, okay, that goes from 1 to 5 and from 1 to 4. Say it's an ellipse, right? So the top part and the bottom part, the left part and the right part. You state the boundaries, and then you can identify your domain and range from those, right? So x, 1 to 5, boop, 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 boop. Range 1 to 4, y in the middle, boop, 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 boop. Again, the only way you're going to get these guys is just practicing. Hopefully that helps a little bit, and we'll work out some stuff in class. Thanks.